Let us look at this from this angle. We would like to be able to run multiple processes, as many processes as we can, within whatever physical memory we have. And we would like the physical memory to actually fill up with something useful, like the pages of the processes in execution. So we have these multiple processes, like 3 in our illustration, and the physical memory is filled with the pages of their processes, those pages that they appear to be needing at the moment. So we have some yellow pages in it corresponding to P1, we have some green pages in it corresponding to P2, and so on. Okay. Now suppose that some process like P2 references a page that is not mapped into physical memory. This is a legitimate page, so the system has to accommodate it, has to accommodate the demand. So the system must find a frame of physical memory where the image of this page should be put and simply allocate the page to the process. Now the question is where to find such a frame. There is no free frame. So one of the pages that are present in memory must be swapped out. And the swapped out page, the page to be swapped out to make room for a newly demanded page, is called the victim page. Now, how to select the victim page? Well, there's one obvious criterion of performance. The system should select the victim page in such a way as to make sure that it won't be needed for a long time. Well, the system cannot really make sure, because the system never knows which page a process is going to demand. So the system can only guess. But the system can guess more or less intelligently. So I would like to, at least statistically, to be able to tell whether a page stands a good chance for not being needed in the immediate future or not. Mind you, if the system makes a wrong decision, like it selects a page that will be needed in a short while, for example, it may decide to remove this page of process P1. Now, if it happens that P1 immediately needs that page, then of course the selection was wrong, because there is some cost, there is a cost of replacing those pages. The whole idea only works under the assumption that the faults do not occur too often, that processes basically run smoothly. What it means, it will become clear in a short while. But for now, intuitively, the idea only makes sense if the processes run smoothly. So process runs for a while, then may hit a page that is not present in its address space, so the page has to be brought in. Bringing in a page almost always involves disk transfers. This is a considerably more complex, more costly operation than just making a regular memory reference when the page is present, right? So there is a serious cost involved. The pages should not be brought too often. So the idea is, as always, to hit some middle ground. There is, obviously, processes don't need their entire address spaces at once. They can live comfortably within some confines. But then, if we push things too far, then they will generate too many page faults and they will slow down. As I said, we'll talk about this more formally, but for now, the intuitions. So the system should be intelligent about selecting the victim page. The system never knows for sure. This is a fact. But the guess should be guided by some wisdom. I'm going to mention one more requirement for the hardware, needed for the things to be doable and sensible. So in this context, it may make sense to say again what I said already when we were talking about restartability of instructions, about side effects of instructions and the restartability, that the instructions provide the grain at which events like page faults happen, provide the grains at which the program can be restarted and continued. Okay, so we have the list of instructions executed by the program. At some point, some instruction may cause a page fault. Then what the system is supposed to do is to fix the problem, whatever problem is indicated by the page fault. In the context of what we are discussing now, it may involve fetching the page, bringing the page in, and adjusting the mapping. And then the only thing that can be done is to re-execute the offending instructions. So the instruction boundaries, specifically what can be pointed to by the program counter or the instruction counter, provide the finest granularity of action. It's the granularity at which events happen and at which the recovery after an event can be carried out. And here we have that postulate, that required property of the CPU hardware, specifically of the set of machine instructions. Okay, now we're talking about confining the amount of memory used by a program in execution. So we may have a program that in principle may need a large space to run, but at any moment it needs a small fragment of that space. So the system may, for example, decide how much physical memory the program should get in order to live comfortably within that amount. And the system may say, okay, I will give you 256 memory frames, and you are supposed to live within that area. Whenever you need a page and you are already using your 256 frames, I will remove one of your pages such that you never exceed that limit. Okay? So the question is, what is the absolute minimum on the number of frames that the process must have in order to be able to execute in a single go the most tricky, the most complicated instruction? The problem is this, like, so instructions, well, we already talked about it, but in a slightly different context. Instructions may be complex. An instruction may require a whole bunch of operands in memory. Okay, so we talked about side effects. An instruction may have done something to its environment before it hits a page fault, and then it is impossible to restart the instruction. But there's another issue. Like, suppose that you have a complex instruction that requires that takes a lot of operands in memory. So the system may the program may execute the instruction, and the instruction may fault at some point. So the system will bring in the page that has caused the fault. Okay, but while doing so, the system may have to remove some other page of the process because there is no room. Like, the process is supposed to operate within some confines, and the process is exceeding its limit. So the system has to remove one of the pages owned by the process and bring in the page that causes the fault. And now try the instruction again. The program will try the instruction again. The system restarts the program tries the instruction again. There's another fault. Because while fetching the page demanded last time, the system had to remove one of the pages that is still needed by the instruction. So there is a fault. The system removes another page belonging to the process and brings in the page that caused the fault. And then it tries the instruction again. But it has removed some other page needed by the instruction. What I'm trying to say is that there may be instructions that in order to be executable in a single go, which is always needed to complete the instruction to the very end, require too much memory to be mapped at once into physical frames. And then it will be impossible for the system to come up with a reasonable bound on the amount of memory needed by the program. Like, for example, suppose that we have this, we already looked at this instruction that takes one operand from memory pointed to by an address, takes another operand in memory pointed to by an address, adds the values of these two operands, say interpreted as integer numbers, and stores the result at a third memory location. Okay? The question is, how many frames are needed for this instruction to execute successfully? Let me see, okay, what does it mean? Like, the instruction needs 4 things to be present in memory to execute. It's code. The code must be there because the CPU must fetch this code for execution from memory. So the instruction code must be in memory. The first operand must be in memory. It can be anywhere in memory, right? The second operand must be in memory, and the target must be in memory. Because instructions are indivisible from the viewpoint of triggering events and being restartable, all 4 components must be present in memory at the same time, because otherwise the instruction will not be able to execute. Now, so the minimum number of pages at first sight is 4, right? Because the instruction image must be present in memory, and it can be, well, it can be allocated in any page whatsoever. This is actually a code page, so you know that it is separate from data, right? Then the first operand must be allocated in some memory, so it is 1 page. Now, all 3 operands may fall into different pages, right? If we are lucky, they will fall into a single page, right? But there's nothing preventing them from falling into different pages. So there are 4 different locations in memory that are all needed in order for the instruction to be executable. Now, say, if, for example, the system says, okay, I will give you just 3 frames of memory and you are supposed to live within this area. When you need a 4th, I will victimize one of your pages and such that you never exceed 3 frames, right? So then the instruction won't be able to execute. Because, like, for example, the frame with the first operand is absent. So we fetch the instruction, we are lucky, the page is present. Then there is a fault on the page on the first operand. The system will bring the page, but it will have to remove one of the remaining pages. So, for example, it will remove the code page. So then there will be a fault on the next attempt to fetch the instruction. Yeah? See what I mean? On every try, the instruction will fail, will generate a fault, because one of the 4 components needed for the instruction to execute will be missing. Now, it is probably even worse than that, because those operands, those parts are often allowed to cross page boundaries. Some architectures require alignment, but for long operands, practically all architectures admit crossing page boundaries, which means that if we are really unlucky, then the code of the instruction will cross a page boundary. The first operand will cross a page boundary. The second operand will cross a page boundary, and the same about the third operand. And they may cross different page boundaries in different places of the address space. So in the worst case, we may need 8 frames to be able to execute a simple instruction like this. Okay? This is normal, and this is not a big deal. No sane system will insist on allocating to a process less than 8 frames. Okay? Usually the number is like, well, thousands, at least hundreds, right? It is a small program with well-contained, with good locality, right? But this illustrates that the problem is there, because, well, this is a simple instruction after all. Who knows what other more complicated instructions are there, and what is the limit? And the system would like to know. The system would like to know, because if there are tricky instructions that require a lot of physical memory to be present and allocated to the process in order to be executable, then of course the system should know that, because it should know that it shouldn't allocate to a process any less than that minimum. Okay? Here we have a historical example of a computer architecture that was extremely and anecdotically unfriendly from the viewpoint of virtual memory. The architecture featured an addressing mode where you could have the address of an operand, and if the leftmost bit of the address field was 0, the address was simply treated as the address of the operand. Okay? But if that bit was set, the address was treated as the address of the operand. And if that address had the I bit set, then, well, you guessed it, the idea applied recursively. So you could provide this as an argument to an instruction, and the instruction would go through all these links to get hold of the actual operand at the end. But the programmer could in principle create a list spanning the entire address space with those pointers, which would mean that the instruction needed the entire address space to be mapped into physical memory in order to execute. So there was no way to contain the memory requirements of a program, because in the worst case, the program could need its entire address space to be mapped into physical memory, which would make the whole concept of locality pointless. Okay? So those guys realized this when they tried to implement virtual memory on that system, and then they had to limit the length of this list. I don't remember what kind of limit that came up with, but it was probably something like 8. Okay, so now about the arguably most important part of memory management, of contemporary memory management techniques, page replacement policies. Okay, so where are we? We are talking about virtual memory. Virtual memory is the concept where a process only uses a fraction of its memory, a fraction of its formally required address space based on the concept of locality, assuming that it only needs so much at a time. If it needs more, then it will demand. It will demand by simply referencing that memory, and its demand will be fulfilled automatically by the operating system by fetching pages from wherever they are, putting them into frames of physical memory, adjusting the mapping, and restarting the process. The process is not aware that there was a problem at all. Okay? This happens automatically. It is called virtual memory because portions of the program's address space are virtual. They're not present in physical memory. They're kept in secondary storage, in backing files, like in the executable, if they are code pages, or in some swap area, in some file on the disk, where the system keeps those data pages of processes that have been swapped out. Okay? Now, page replacement policies are about the strategies of selecting victim pages. So if free frame should be vacated in physical memory and a page should be victimized, a page should be removed. How to select the victim page? How to select the victim page such that the likelihood that it is going to be needed in the immediate future is minimized. Okay? The goal is to find the page that is the least likely to be needed in the nearest future. The measure to maximize is the time during which the victim page will not be demanded back. This interval determines the page fault rate in the system. determines the frequency with which programs generate page faults. It will make good, smart decisions, then the page fault frequency will be low and they will be sparse. If we made poor decisions, then the pages that were victimized will be demanded back very soon and the page fault rate will be high. If it is high, then it is bad, because to service a page fault, we need to do disk transfers. Okay, programs wait for pages, cannot proceed. We have to fetch them. It takes time because we transfer them from the disk, at least in most cases. Now, we have to realize that no matter what we do, no matter how smart we try to be, it is all just a guessing game. You never know what the program is going to do. Okay, so you can, in particular, you have write a malicious program that is referencing memory in such a way that it fools the page replacement strategies and its performance always appears poor. There's no point to write such programs other than for pranks, but you can do this in principle if you know how the page replacement strategy works. The idea is that normal programs behave decent. They behave in according to some patterns, and those patterns are reasonable. Okay, but first a few sort of more general observations. Suppose that we have found a victim. Now, the question is, what is the cost of victimizing it, of actually removing the page? There are two possibilities. The victim can be clean or dirty. What does it mean that the victim page is clean? It means that the copy of the page in secondary storage, in its backup storage, is up to date. The page hasn't been changed by the program since it was brought in. For example, we know that some pages are always clean. The pages that belong to the code segment or constants, the same thing, right? What is good about clean pages? A clean page can be victimized fast because we don't have to write it back to its backing storage. We don't have to write it back to the disk. Because now we know that its copy is up to date. Like when you have a code page, you know that it is never written into. So its standard backup copy in the executable file where it was fetched from to start with, that copy is up to date. So code pages don't have to be sent back. They are always clean. Victimizing them is easy. Just remove them. Okay? But some other pages, well, it is legitimate for a page to be dirty. A data page is often dirty because the program has written something into it, right? So one important thing is to be able to tell. If the system can tell whether a page is clean or dirty, it knows whether it should bother writing the page to secondary storage or whether it can just unmap the page and forget about it. Okay? So how does the system tell? Well, page table entries, when you backtrack all the way to the slide on which I showed you this page table entry for the x86 for the first time, you will see a bunch of flags that we mentioned a few. There is a bit called D, which stands precisely for dirty. This bit is set when the page described by the page table entry is written into. Yeah. So now, when the system brings in the page, it will clear this bit in the page table entry. Later on, when the system looks at this bit and it sees that the bit is set, it means that the page has been written into by the program. So the page is dirty. So the cost of victimizing it, well, is higher. The page has to be sent to its backing storage. This bit may be called differently on different architectures. So just for diversity, here is a page table entry from VAX11. And the bit is called M. M for modified, right? Okay, so how to select the victim? If we are short of ideas, we can always do it at random, instead of blindly. We need a victim, let's just grab a page at random. This one is easy, but it's not very smart. Then one can think this way. Okay, if we are not sure how to select the victim properly, at least we know that some victims cost more than some others. For example, a clean victim is easier to victimize. So let's improve upon this naive strategy. Call it random replacement plus. The victim is selected at random, but from among the clean pages. We don't know how to do it right, so at least try to do it cheap. If it happens that all pages are dirty, then we will select the victim at random from the dirty pages. So I want to tell you right away that this kind of approach is stupid. It is by far more important to come up with a good guess as to whether the page is going to be needed or not, and select pages that are not likely to be needed in the nearest future, than to look at secondary aspects of victimizing the page, like the cost, like whether we have to write it to the disk or not. Then, if you follow this kind of approach, that you prefer to victimize clean pages, then after a while you will remove all the code of your program, because the code pages are always clean, they never get dirty, so they will never get into the competition with dirty data pages, right? They will tend to be removed first. So the important principle is to focus first on finding a page that is likely not to be needed for a long time, or that is unlikely to be needed immediately, right? This is way more important. So first we look for a good victim candidate, and then we worry about the cost of removing it. And here we have a simple and reasonably sounding strategy. You need a victim? Select the oldest page, the one that has been in memory for the longest time. First of all, this strategy is very easy to implement. How do we implement it? Well, the system needs some data structures to keep track of the status of the pages that are mapped to programs and so on. So we can assume that the system keeps a list, maintains a list of pages, they are linked. It's not exactly pages, but some data structures representing the pages for the system, but we can use the shortcut, right? The system maintains a list of pages, and the first page on this list is the page that has been in memory for the longest time. When a new page is brought in, the page is added at the end of the list. So it works like this. When the victim is needed, the first page in the list contains the oldest page, the one that has been in memory for the longest time. And when a new page is brought in, its description is added at the end. Simple like that, okay? So, because new pages are added at the end, by the time the page gets to the front, it becomes the oldest page, okay? And it is a cheap and simple strategy, because there is some action to be performed only when there is a page fault. When there is a page fault and we need a victim, we look into this data structure, and then we remove the first entry from the list, which is always a very easy operation. It costs constant time, completely trivial. Comparing to the fact that when there is a page fault and we need a victim and we need to bring in a page, we have to do a disk I/O. This is a much more serious operation than any cost that we can think of related to fooling with this simple data structure. Okay, so it is a simple strategy, very easy to implement, and there is some good motivation behind it. You are removing the oldest page. You can say, okay, if a page has been in memory for a long time, then if the process wanted to explore its contents, well, The process has had ample time to do it. Okay? Makes sense. Unfortunately, FIFO is not perfect. It has a rather painful flaw. It does not account for permanently needed pages. Okay, what am I talking about? Like, let's look at this piece of code. It is simple enough to illustrate the point. Like, here we have a program in which we see a loop, and in this loop we use some huge array, okay, and we scan through this array, and there may be some other calculations. So while we scan through this array at different moments during the execution of this loop, we may be looking at different portions of the array. But no matter where we are within the array, we always need I and we always need sum, because we use those variables to compute something within the loop all the time. So even though we change our locality as far as this huge array is concerned, we always stay within the locality of these variables. Those variables are needed all the time. So now imagine that, well, those variables are declared somewhere, like here, so they fall into some page, right? They fall into some page. At some point, this page is brought in. And now, no matter how heavily those variables are used, when the time comes, when the page becomes the oldest page, it will be victimized, okay? So the only criterion for victimizing pages with FIFO is the age. How long the page has been sitting in memory. The page may have been sitting for a long time, and the page may actually be needed because it contains some variables that are needed all the time. So from the fact that something is old, that something has been sitting in memory for a long time, does not, we cannot tell that something is not needed. Okay? So here is a better one. Least recently used. With this strategy, we victimize the page that has not been touched by the program for the longest time. So note the difference. For FIFO, we would just look at for how long the page has been sitting there. Okay, like nobody worried about whether the program has touched it recently or not. Now we say we will victimize the page that has not been touched by the program, has not been used for the longest time. Now we can envision some implementation of this strategy conceptually. Let me say, okay, we have a list like this, and now whenever a page is referenced, wherever it is in the list, we will grab its description and we will remove it from its current place and add it at the end of the queue. Okay, so at the end of the queue, we will see pages that have been referenced recently. Whenever a page is referenced, it is grabbed from its current place and moved to the end of the list. Okay? Of course, I'm not talking about pages, but some data structures representing them. This way, the front of the queue will hold the page that hasn't been used for the longest time. What will tend to bubble to the front of this list will be the page that hasn't been touched for the longest time. Because whenever a page is touched, it is moved to the end, right? So this one must be the one that hasn't been touched for the longest time. Okay? But let's clearly see the difference between FIFO and LRU. For FIFO, we postulated some action to be carried out when a page is needed, when we have to do something like actually replace a page. Only then had we to consult the data structure and look at the first page and so on and play with the pointers. Now we are postulating something to be done whenever a page is referenced, which is a completely different story. When a page is referenced, we don't receive, like nothing happens. The program is just referencing pages. So there's no interrupt, no fault to which the system is supposed to respond, and then it can safely and freely look at whatever data structures are needed, because its action is going to be expensive anyway. It has to fetch a page from secondary storage and possibly write some other page back to its backing storage. Now we want something to be done at every reference of the programs to memory, and this is, well, I don't know how to do it. Okay, and you would have to implement this structure in hardware and use some extremely sophisticated hardware such that the operations of this structure do not compromise the sort of speed of memory references. It cannot be done. Okay, so the bottom line here is that this is a nice structure, because it actually tries to find a page that hasn't been used for a long time, but we cannot really implement it exactly, because we would need to do something prohibitively expensive at every memory reference. Systems try to approximate LRU, realizing the flaws of FIFO. FIFO is extremely easy to implement, and it is not without merits, and it can be tweaked into a decent strategy, as we shall see. But the general idea is to try to approximate LRU. So for that, you would have to know whether a page has been referenced recently or not, without having to perform complicated actions on every memory reference. If we cannot perform a complicated action on every memory reference, then perhaps our idea of approximating LRU will be based on some observations that are done at some sparse intervals by the operating system, perhaps where it has nothing better to do, such that it doesn't compromise the normal efficiency of programs, right? So for that, the system would like to know whether a page has been referenced, say, within some time interval. Like, contemporary hardware facilitates this kind of observations. Again, when we look at the format of the page table entry on the x86, we see a bit there, and this bit is labeled A. What does A stand for? Accessed. Okay. And what is the idea here? Well, the system may clear this bit at some moment, and if it looks at the bit later after a while and the bit is 1, it means that the page has been referenced in the meantime. So there was a reference to a location within the page. So this is in addition to D. Remember, D is set when there is a reference to the page and the reference is for writing. So the page has been written into and the page is dirty. Okay? But A is set when the page is accessed, which means that it is set both on write and read accesses. So again, the system will clear this bit at some point, and then later on it will look at this bit. If it sees that the bit is 1, it means that the page has been referenced in the meantime. This may be a far cry from implementing LRU, but it at least can give the system some idea as to which pages are being referenced and which are not. Okay? This is a very important thing to know, very important thing to tell by the operating system. So contemporary architectures implement this bit in hardware, but even if this bit is not implemented in hardware, it can be emulated with a reasonable effort. For example, here you have the historical architecture on which the bit was not present in hardware, but it was emulated. And how do we emulate the accessed bit? Sometimes it is called referenced bit. Okay, on the 370 it was called R for referenced. So how can it be emulated? Well, instead of clearing the reference bit, the system will mark the page as invalid without evicting it. So when the page remains in memory where it was, it is not victimized, it's not removed, it is just marked as invalid. The system knows that the page is valid, but it has been marked as invalid. What for? Such that when the program references it, there will be a fault. So the program references it, there is a fault, the system changes the status of the page to valid and marks in its own data structures that the page has been referenced. Okay, so for example, on the VAX, we could use one of the unused bits for the R bit maintained by the system. Okay, so you say, okay, this is expensive because in this case this bit is set automatically by hardware when a reference is made to the page. Here on a reference there is a fault, but it's on the first reference only. Okay, so the system, after the fault, the system changes the page to valid. So if there are more references to the page, they will go smoothly. Okay, there is some cost, true, for emulating the bit, but the fault will only occur on the first reference. And there is just the cost of the interrupt. There's no need to fetch the page from anywhere because it is there all the time. So all the interrupt service routine has to do is to adjust the mapping to make sure that the page now appears as valid. Okay, it's clear? And here we have the winner. Second chance. Okay, FIFO is simple. Well, one would say it is trivially simple. LRU is impossible. Okay, but let's try to strike a compromise. Okay, so how is this compromise going to work? Well, it all starts like FIFO. The pages are put into a list, and whenever a page is demanded and brought in, its description is added at the end of this list. At the front of this list is the oldest page, so the prospective next victim, but we add a little twist. The first part of the twist is that now we take into account the access bit or reference bit, as I prefer to call it. Okay, so this is the bit that is set when the page is referenced. And now we go like this. We look at the victim at the front of the queue, as for FIFO. But if the reference bit or the A bit, well, it's difficult to avoid confusion because different architectures, different people use different names for the same thing. But this is normal in operating systems because there are different architectures, there are different manuals, there are different vendors, and vendors tend to confuse people such that they never know what they are buying, right? So if the reference bit or the A bit or whatever it is called of the victim candidate, like the oldest page, in this case is 1, this means that the page has been referenced. Then the candidate is moved to the end of this list and its reference bit is cleared. And we look at the next element. And we keep going until we find the first page whose referenced bit is 0. Okay? Perhaps a more natural way to visualize this strategy is to loop this list into a circle and imagine that there is this hand pointing at the front of the list. Because when we look at the front and we see that the reference bit is set, we move the page of its description to the end of the list, then it looks like moving this head around a circular list. This is the front of the list and this is the tail. When we move the hand, we don't have to actually move the front item to the end of the list. It happens automatically, right? So this is sometimes it is called the clock strategy. Okay, so we have this hand pointing at the front of the list, and we look at the reference bit. If the reference bit says that the page has been referenced, we set it to 0 and move to the next item. Once we hit the item whose reference bit is 0, we pick it for the victim. So, the worst that can happen is that we will have to make a full circle to this list if all the pages are referenced. If all the pages are referenced because the processes sweep their address spaces back and forth, right? Then we will end up degrading this strategy to FIFO, but there is an important difference. The page that normally would be victimized by FIFO gets a second chance to prove its relevance. If there are pages that are not being referenced, they will be picked ahead of pages that are being referenced. Because once a page is moved to the end of the list, this hand has to go through all the remaining pages before it arrives again at the page. And in the meantime, if the page has not been referenced in the meantime, well, too bad. It is a good candidate for victim. But, for example, if you have one of those permanently needed pages, it has all the time there is to prove its relevance. Okay? So if the program really needs this page desperately, by referencing it all the time, it will for sure reference it. So it will keep the reference bit of the page lit, and the page will never be removed. Okay? So why is this a good compromise? Because it is simple. We still have an action that is only carried out when we need something, like there is a fault, and those bits are usually set automatically by the hardware. Okay? And if not, they are emulated, but tough luck. On most architectures these days, those bits are set by hardware. So we have the simplicity of FIFO with this, not exactly LRU, right? But owing to this second chance trick, the permanently needed pages are saved. And how do those strategies compare? Well, second chance is not bad. This is the short conclusion. Now, here's a graph. Some long time ago, I was studying the performance of page replacement strategies in some specific context. This is not important, but here we have a sample graph that compares three strategies: FIFO, second chance, and LRU. Well, there's no exact implementation of LRU, but this was simulation, right? In simulation, we can do whatever we please. So this is exact LRU in a simulated environment. And how are those strategies compared? Well, there was a program. This was a sorting program, which here n is the number of keys to be sorted, and the program was executed in 25% of required memory. What does it mean? So there is some memory required to accommodate the program. If the program was given 100% of its required memory, then it wouldn't generate any faults. It would have all memory that was needed by the program. So there would be no need to replace pages. Okay? It was a single program, run at 25% of its required memory, and the amount of required memory is determined by the number of keys to be sorted. And there were no other programs, so this was the only program generating faults. Okay? So what was measured was how many faults the program would generate over its lifetime when solving the problem, and the number of page faults was divided by the size of the problem to be solved, so that this is normalized. It is not surprising that, despite the fact that the size of the problem grows, these curves look pretty much like flat lines. Okay, so again, what we have here is the number of page faults, and this number is normalized to the size of the problem. And of course, the higher this number, the poorer the strategy. Okay, because we would like to minimize the number of faults. The whole idea of finding a good victim is to minimize the number of page faults. So obviously LRU is the best, right? FIFO is the worst, and there is a significant gap between FIFO and LRU. Okay, no surprise here. but we can see that the second chance is quite close to LRU. So for its price, it is a very good approximation of LRU. So second chance is the most popular actual strategy used in actual systems. Well, we'll see that the issue is a little bit more complicated, because in actual embodiments, the page replacement strategy is part of a sort of larger scheme of things, and we will get there a little bit later. So we've been looking at the issues from some simple and clean perspective, but it's actually important to approach those issues from this clean and simple perspective, because the observations that we make while doing so are actually valid and underlie the actual solutions, even though they are more intricate and more complex. Then, the policy is not all. With multiprogramming, it is also important how to divide the available physical frames among multiple processes. Okay, so now we have to look now a little bit more formally at the issue of performance, and we have to dive into a tiny bit of theory.